In this lesson, we're going to introduce texture filtering. Texture filtering applies to techniques that we can use on the GPU to improve the quality of our texture rendering. So take a look at the texture filtering modes demo in lesson 4.3. What this is doing now, and gone are the wrapping modes enumeration, replaced with an enumeration for the filtering mode. There is a variety of filtering modes. There's filtering mode point, filtering mode linear, filtering mode point, mip-map point. Let me describe what some of these things are. What happens when the image is magnified based on its relationship with the camera and its authoring resolution? Your camera is going to be positioned either to the point where it's minified, it's smaller than the original resolution of the texture, or where it's magnified. That's called magnification and minification. So what we have to do is tell the GPU, when we say, this is the color of a pixel, sample that, and it's magnified and zoomed into that texture to where the texture doesn't have an actual texel at that position. What happens? Or conversely, when we have the same pixel is actually covering multiple texels, what do we do? And filtering is the way that we address that in OpenGL. So filtering has a variety of techniques. The first one is point filtering, also known as nearest neighbor filtering. This is the cheapest, the quickest, least expensive, but it also produces the worst results. The point filtering says, if I don't have a texel at the given UV, then give me the nearest one to it. So it doesn't attempt to actually blend any of the surrounding texels at all. It just says, give me the nearest one. Linear filtering does linear interpolation between two texels. So it finds an in-between texel and then it interpolates between the two surrounding that texel. Now this is true for both the U and the V. So what we actually see when we see linear filtering is bilinear filtering. We actually see two linear interpolations. Now with filtering, we also have a problem with minification, where when something gets further away, we have one pixel that maps across multiple texels. How do we deal with that? One way to deal with that is to generate a set of mipmaps. And I had alluded to this in lesson 4.1. You saw where the soil library specified a generate mipmaps flag. Well, mipmapping, and I'll pull up an image that describes mipmapping, looks something like this, where we have an original texture, and then the mipmaps for that texture are divisions of 2 all the way down to a 1x1 texture. Now, all of these can be stored in the same texture, or they can be stored in individual files. It depends on the file format. So let's say that when we zoom far enough away from a texture, when we use mip mapping, what we can do is pick the appropriately small texture corresponding with the distance from the camera. And the reason that we'll do that is that, yes, we can generate mip maps automatically. We can also have an artist generate mip maps. But instead of us just blindly or without forethought dropping out texels from the texture, we can do interpolation at the time of creation. Yes, it increases the size of the texture, but we can get some better results when we minify the texture. So that's what mip mapping is all about, is as we get further away from the texture, which mip level do we choose? Mip level 0 is the highest mip level, and the number of mip levels that you have depend on the original resolution of the texture. The next couple of filtering modes that you see here deal with mip mapping. Point mipmap point specifies that we're going to do point filtering inside of the given mipmap, and then we're going to do point filtering between mip levels. Now, linear mipmap point means we're going to do point filtering between the mipmaps, but we're going to do linear filtering for the selected mip level. Point mipmap linear means we're going to do point filtering for the selected level, but we're going to do linear filtering between the mipmaps. And then trilinear filtering, which is the highest quality filtering that we're going to use here, allows us to do bilinear filtering between two mip levels, and then we're going to do linear filtering on the final results of the two bilinear filter processes. Between the two mip levels, we'll do linear interpolation between those to produce a final result. So let's look at how this is used in action. You'll notice that the rest of the demo has very similar code to the previous one. We have the same set of texture samplers. We're going to build up a set of texture samplers for the number of filtering modes that we have. And then we're going to build up a map to associate every one of those texture samplers to their given filtering mode. All right. Finally, an active filtering mode, and then we're going to be able to toggle through that with the keyboard handler. So inside of the initialize method, we're going to load our filtering modes, vertex and fragment shaders. And again, these are identical to the previous two vertex and fragment shader demos. The difference then, of course, is that we're specifying a different set of samplers that go into the fragment shader. It's the same creation of the vertex and index buffers, but now this time around, we're going to call glgen samplers to call our texture samplers, and this time around we're going to specify for all of the different filtering modes a different set of parameters. So GL sampler parameter I for GL texture min filter and GL texture mag filter. So the min and mag filters are what we're talking about when we talk about minification and magnification. So we can specify different options for minification versus magnification. Now, GL nearest means point filtering. So when we specify GL nearest for both min and mag filtering, whenever the camera is far away or whenever the camera is close up, we're going to do nearest neighbor filtering. We'll find the pixels that surround most closely. We're not going to interpolate between them. We're going to pick the one that is near. And you're going to see what that actually produces. That's going to produce a blocky look when we're zoomed into the texture. Now for the next, we're going to do linear filtering. So this is actually called bilinear filtering. We're going to do min and mag filtering using bilinear filtering. That will do an interpolation between the surrounding pixels. And then the rest of them. So nearest mipmap nearest. So point filtering for the selected mipmap, point filtering between the mipmaps. We're going to do linear mapping for the selected mipmap and point filtering between the mipmaps. Nearest linear means we're going to do nearest or point filtering for the selected mipmap and linear filtering between the mipmaps. And then finally, GL linear mipmap underscore linear, that is trilinear filtering. So linear filtering between the mipmap levels and bilinear filtering on the two selected mipmaps that we'll do a final interpolation between. The VAO is set up identically as before. I just have a little output filtering mode that throws out to the output window what the active mode is. And you can see that. I'll pull up the output screen so you can see that. It just saves us from having to render a font to the screen. We'll just throw some debug information to the output window. This time around, whenever we press the space bar, we're toggling through the filtering mode and setting the active filter. The draw is identical. There's no difference at all here, except for that instead of binding wrapping texture samplers, we're binding filtering samplers. And of course, we can specify multiple parameters. I'm just isolating the two demonstrations here. You would specify both wrapping modes and filtering modes simultaneously. Let's see how this works. All right, so here's our earth texture. And our earth texture, this time we're mapping from 0 to 1. I'll hop back over here. So 0, 0 in the upper left-hand corner, 1, 1 in the lower right-hand corner. And so now we have our earth texture that was otherwise mapped to a sphere, mapped to this quadrilateral. So when I back up, you can see there's some artifacts there. It looks a little strange because we're using filtering mode output. If you look in the output window down there, you'll see active filtering mode, filtering point, mode point. And as I zoom in, it gets very, very blocky, right? The individual pixels that we're doing there, we're doing nearest neighbor sampling, that point filtering sampling. So we're not going to get a nice, smooth interpolation between texels. But if I press the space bar and I toggle, notice now, dramatic difference between point filtering and linear filtering. And when I zoom out, you won't see those artifacts as you did before, the dominant artifacts. Even better when we use mip mapping and linear interpolation. So this is point mipmap linear, and then this is trilinear filtering, which is the best type of filtering that we can get. You can see that the artifacts as we back up get much, much less. And as we zoom in, they're as good as they can get, right, with trilinear filtering. Now, anisotropic filtering would just be an extension in OpenGL that we could enable. And all we would do here with anisotropic filtering in order to demonstrate it would be to move this quadrilateral at an oblique angle to the camera. So if I do that now here, I'll just move the camera up. Anisotropic filtering would actually make that look a little bit better. It wouldn't look as fuzzy as it gets out. Do you see how that gets a little fuzzy as it gets further or more oblique to the camera? So that's what anisotropic filtering would address. So I'm not demonstrating that here just because it requires me loading an extension, but that's another option that you have is anisotropic filtering. And I encourage you to commingle the wrapping modes and the filtering mode into a demonstration on your own and examine the results.